All right, if I got everything, I got, oh, Schmidt, we are on the air. And in today's journey into the dark art of linear algebra, we shall discuss the Gram-Schmidt process, which we can use to accomplish one specific task. Namely, if we are working in some subspace of Rn, and we have a basis for that subspace, then the Gram-Schmidt process will take our basis and upgrade it to a better version, a nicer basis for the subspace, namely an orthonormal basis for the subspace. We like orthonormal bases because they're very natural for geometry. The familiar formulas for dot product and length of vectors in terms of their components work when we have an orthonormal basis. As we saw last time, projections are easy when we're working with an orthonormal basis, and so on and so forth. But that's what the Gram-Schmidt process does. In the book, I imagine Gram and Schmidt as two men working in an orthonormalization shop. You bring them some old basis whose vectors are all sticking out at strange angles and weird lengths, and for a small fee, they will get out their tools and knock it into shape, ultimately handing you back a beautiful orthonormal basis, all of its vectors mutually perpendicular and unit length. So in this lecture, I am going to show you exactly how Mr. Gram and Mr. Schmidt do their work, that you too can open your own orthonormalization shop. And as a little bonus, I also want to discuss something called QR decomposition. You've learned about eigendecomposition as a way of factoring matrices, some matrices anyway. Well, QR decomposition is another way of factoring a matrix, which can be useful in certain situations. I'm going to talk about it in this video because it is directly related to the Gram-Schmidt process. In fact, Gram and Schmidt will be happy to carry out QR decompositions of matrices for you as another service they offer in their orthonormalization shop. But we'll get to that in good time. Let's begin with the Gram-Schmidt process itself. To upgrade an arbitrary basis into an orthonormal one is computationally a slog, but conceptually very easy. Let's begin by formally stating the problem to which the Gram-Schmidt process will be our solution. So the problem is, given a basis crazy A consisting of the vectors a1, a2, all the way down to ak for a subspace of Rn, upgrade it to an orthonormal basis that I will call crazy U, and whose vectors I will denote by u1, u2 up to uk. I've put little hats on these to remind us that these are supposed to be unit vectors, and of course they are also supposed to be orthogonal to one another. Okay, that's the problem. Our solution, which will be the Gram-Schmidt process, is something to which we can simply follow our noses by drawing pictures and thinking about what's going on. This picture is a little bit in my way, so let me move it. Okay, that's better. And while I'm here, let me go ahead and erase the orthonormal basis, because that, after all, is the thing we are trying to construct. All right, how are we going to do it? Well, the first vector in our orthonormal basis is going to be real easy to construct. To get vector u1, all we are going to do is take the first basis vector from the original basis and normalize it, divide it by its own length, so that if I started out with a vector that was 12 units long, just take a 12th of that. And now we have a vector in the same direction, but unit length. We don't have to worry about the orthogonality condition yet, because there's only one vector. When we get to u2 and u3 and so on and so forth, we'll have to design those to ensure that each one is perpendicular to the ones that came before. But there's nothing to do about that here, because this is the first one. So anyway, vector u1 is simply the given vector a1 divided by its own length. So far so easy. But what about our next vector, u2? The only real question is how to get a vector in this subspace that is orthogonal to vector u1. We don't care about the length, because once we have any vector that's perpendicular to u1, well, we can just normalize it and make it unit length. So how are we going to do it? Well, this is where the idea of projection comes in nicely. In the last video, we talked about how we can take any vector and easily project it onto a unit vector, or rather, the line spanned by that unit vector. So let's do that here. Let's think about taking vector a2 and projecting it onto this line spanned by u1. When we do that projection, we get this nice right angle, which is just the sort of thing we want. But anyway, let me write in a picture of our projection vector. That guy is the projection of a2 onto u1, but we saw last time that since u1 is a unit vector, this projection takes on a very simple form. It is nothing but this, a scalar multiple, obviously, of u1, since it's lying on that line, and the scalar itself is just going to be the dot product of a2 and u1. Okay, Well, now we're almost there. Obviously, that's not the vector I want, but what I do want is something like the vector that points from the projection's tip to the tip of A2, something like this guy. And of course, that is going to be the difference of these two vectors, A2 minus A2's projection onto U1. The reason for that subtraction is clear geometrically. From the definition of vector addition as tip to tail, we have the orange vector plus the yellow vector is the white vector. But if orange plus yellow is white, then yellow is white minus orange, which is exactly what we have right here. And this yellow vector is pointing in the right direction because it is perpendicular to our first U basis vector. The only problem is its length. We want it to be unit length, but that's easy. All we do is normalize it, divide by its own length. Like if this thing is only 1/3 of a unit, divide by 1/3 is equivalent to multiplying by 3, and it will be the correct length, 1 unit long. So to get our second basis vector in our orthonormal basis, we're going to take this guy that we constructed, take that vector, and normalize it, divide it by its own length. And that will show up in our picture like so. Aha! Now we have a pair of vectors that are orthogonal to one another and are unit length. This is terrific. And if we were just dealing with a two-dimensional subspace, like in my picture, well, we're done. That's the end of the Gram-Schmidt process. These two vectors would be our new orthonormal basis. But of course, we are not necessarily dealing with a two-dimensional subspace. I stated this in such a way that we're dealing with a k-dimensional subspace where k might be 2, but it might also be 200. So now we need to discuss what to do from here. How do we get the third vector in our prospective orthonormal basis? You know, before we start down that path, let's return for a moment to U2 and rewrite this expression in another form. After all, we said that this projection can be written in the form we discovered in the last video. So if I substitute that in, we would have that U2 is equal to A2 minus, in place of this projection, A2 dot U1 times U1. And then, of course, we have to take that vector, which is the yellow vector down here, and normalize it. That is, divide by its own length. And that's that. Now, for God's sake, do not memorize that thing, or this thing. Instead, whenever you need to work with the Gram-Schmidt process, just draw a picture like we've done here, and it will guide you step by step to exactly the sort of thing you need. Of course, to let it guide you, you do need to know things, like the fact that we can project a vector onto a unit vector in this simple way involving the dot product. You need to know that, but that is something very fundamental that everyone should know. Similarly, you need to know that this vector here, going from the tip of the projection to the vector that was projected, can be achieved through vector subtraction. But again, that's a fundamental fact. It's a basic knowledge for working with vectors. Whereas these sorts of terrifying formulas are not fundamental. They're just built up from fundamental pieces. And look, I know that you know this stuff, but I promise you somebody else watching this video does not. And I need to help that person understand what is basic and what is not. Even if that person is you. Shh, I won't tell anyone. But anyway, let's get back to the business of figuring out what U3 would look like. This would be the third vector in our prospective orthonormal basis that we are constructing from some arbitrary basis. Well, this is supposed to be a basis for our subspace, so if our subspace is going to have 3 basis vectors or more, it is going to have to be at least 3-dimensional. So let me erase this word subspace so it doesn't confuse anybody, because we're not just working with a 2-dimensional subspace anymore. So let's say our basis crazy A contains not only vector A1 and A2, but some third vector, A3, which is sticking out of the plane that we have been working in so far. Well, if we were trying to take A1, A2, and A3 and play Gram-Schmidt with them, turning these 3 linearly independent vectors into an orthonormal set, well, we've already described how to get U1 and U2. How am I going to take A3 and turn it into some third vector that's perpendicular to both U1 and U2? Well, I can play the exact same game with projections. Let's begin by dropping a perpendicular from the tip of A3, or equivalently, I'm taking vector A3 and projecting it orthogonally down onto this orange vector in the plane. And that orange vector, which I am going to call P for short, is, of course, well, it's the projection of A3 onto what? How can I describe this plane? Well, how about as the span of U1 and U2? So our orange vector P is the projection of A3 onto the span of the vectors we've already constructed, U1 and U2. Good, but the orange vector isn't the one we want. What we want is this guy, the vector from the tip of our projection to the tip of A3 itself. That is going to be perpendicular to this plane, and therefore perpendicular to every vector in it, including u1 and u2, which is exactly what we want. So this vector is going to be A3 minus P. It's perpendicular to the plane, and therefore perpendicular to u1 and u2, as we just said, but it's not necessarily the right length. We want it to be unit length. Well, that's easy. Normalize it. Once we do that, we will have the vector we want. I'll place it at the origin, and it will look something like this. So u3, is perpendicular to the plane spanned by u1 and u2, is just a normalized version of this vector. So to write down an expression for it, we could do it in a few different ways. We could say that it is A3 minus the projection of A3 onto the span of u1 and u2. That gives us the right direction, but to get the right length, we need to normalize, divide by its own length. And of course, if we wished, we could rewrite this stuff, expand it out, using what we know about projections from the previous video. So we could rewrite all this stuff, and in place of that projection, we could write, well, what is it? To project A3 onto the two-dimensional subspace spanned by these orthonormal vectors, well, you remember how that works. It's just a sum of the projections of A3 onto each individual unit vector. So first we project A3 onto U1, which gives us A3.U1 times the vector U1. And to that, we are going to add A3's projection onto U2, which of course is A3.U2 times the vector U2. That was what we learned in the previous video. And all these parentheses are making me antsy, so let's distribute that negative like so. Good. That's our vector pointing in the right direction. So now we just have to normalize it. And we are done. Again, this is a disgusting expression. The main thing is being able to understand what it represents and what its various parts represent in terms of projections and why we are dividing by its length. All of these little pieces. If you can put those pieces together, then it's not so bad after all. Okay, and if our basis A consisted of just 3 vectors, so that we were working with a 3-dimensional subspace, then we'd be done. We would have our orthonormal basis consisting of U1, U2, U3, and all's well. But of course, we might not be working in a 3-dimensional subspace. Maybe our subspace is 4-dimensional, in which case we would have a basis consisting of 4 basis vectors. And we would need to come up with not just U1, U2, and U3, but also U4, a 4th vector that is not in the span of these 3, and in fact is perpendicular to the 3-dimensional hyperplane that they span, and unit length. I can't quite draw you a picture anymore, but by this point, I think you understand how it's going to work. So let's see if we can reason it out geometrically. We want U4. Well, what do we know already? We've already established U1, U2, and U3 as a set of 3 vectors that are mutually orthogonal and unit length. They form an orthonormal basis for their span, which is some 3-dimensional subspace of whatever 4 or more dimensional subspace in which we are working. It's also, of course, the span of A1, A2, and A3. But, when we look at A4, that's some 4th vector that sticks out of this 3-dimensional hyperplane. A4 does not live there. It cannot be expressed as a linear combination of U1, U2, and U3. If we're going to play Gram-Schmidt, we have to turn this into a new vector that is perpendicular to this entire hyperplane, which will be the case if it is perpendicular to these basis vectors, U1, U2, and U3, and also it has to be unit length. How are we going to do that? Now, I can't draw you a convincing picture of something taking place in 4 dimensions, but I can at least draw a schematic picture which will guide our thinking and allow us to write down the appropriate expression for U4. Still by thinking geometrically, and not merely by following an algebraic pattern, though of course we could do that too. A4 does not lie in this 3-dimensional hyperplane, but I can project A4 orthogonally onto that hyperplane, onto the span of U1, U2, and U3, and then climb back up the vector from the projections tip to A4's tip, and that golden vector will be perpendicular to this whole hyperplane, and therefore, in particular, perpendicular to the 3 vectors U1, U2, and U3. If we normalize that guy, it will give us U4, because it will have the right length as well. Well, now we can see exactly what that is going to be. That golden vector sticking in the right direction, that goes from tip to tip of two vectors, so it is the difference of those vectors. In particular, it's going to be A4 minus this projection vector, which is A3's orthogonal projection onto the span of U1, U2, and U3. That expression right there is my vector pointing in the right direction, i.e. perpendicular to U1, U2, and U3 in a space of 4 or more dimensions, and now I just need to get it the right length, so I normalize it. And now I can call on what we learned in the previous section to write this in more primitive terms, because I know that to project vector A3 onto the span of these 3 orthonormal vectors, I can project it onto each one individually and add the projections up. So I will end up with, instead of A4 minus this one projection, A4 minus the sum of 3 individual projections. Again, this is one reason we like orthonormal stuff so much. It allows us to turn the projection onto a subspace into the sum of projections onto one-dimensional subspaces. Anyway, that gives me the vector in the right direction. I just need to, well, first, let's distribute that negative, but now we just need to normalize. Yikes, that is a disgusting expression. And yet, it is still a very, very simple expression, as I hope you understand when we think about it conceptually. The existence of the entire denominator is just to make it unit length. The top is just a vector minus its projections onto 3 different orthonormal vectors. All right, that wasn't so bad, was it? Well, that's the Gram-Schmidt process. That is literally all there is to it. Of course, if we were working not in a 4-dimensional subspace of Rn, but a 5-dimensional subspace, we would go on to get U5. And I'm sure by now you understand exactly how that works. You draw the same schematic picture, except now this weird thing in the cloud you think of as a 4-dimensional hyperplane. All the same calculations go through, and you just end up with one extra term here, because you have to project onto not 3, but now 4 vectors that we've already produced. And so on for U6, U7, U8, and so on and so forth as far as you like. All right, and as ugly as these calculations are, I suppose we should do at least one numerical example to show you what this looks like in a concrete setting. So here's our problem. Let's apply the Gram-Schmidt process to these 2 vectors, A1, the vector 4, 0, 0, 3, and A2, the vector 5, 2, 14, 10. So these are 2 vectors in R4. They are obviously linearly independent, since they are not scalar multiples of one another, which means that they constitute a basis for their span, which is a 2-dimensional plane in R4. So schematically, we might think, here's a plane, the plane spanned by these 2 vectors, and here are the vectors themselves. I'm drawing a picture because it will guide our calculations. As I said before, there's no need to memorize anything. So let's work on our solution. Gram-Schmidt is supposed to turn this pair of vectors, which is a basis for this 2-dimensional subspace, into a new pair of vectors, U1 and U2, which are orthogonal and unit length. In other words, orthonormal. How do we get our first vector? U1? Well, that's easy. We just take the first vector in our given basis and normalize it. That will be the first vector in our orthonormal basis. So U1 is simply the normalized version of A1. So we need to divide A1 by its length. Well, the length of A1 we can see is, well, let's see, that's the square root of 16 plus 9. So the square root of 25, which is 5. So A1 is 5 units long. That means U1 is 1/5 of A1, which in terms of its components is going to be 4/5, 0, 0, 3/5. Good, and now we just need to come up with U2. Well, again, there's nothing to memorize. We just think about the picture and let it guide us. We're looking for a vector that's perpendicular to U1 and unit length. How do I get such a vector? Well, we can take A2, project it orthogonally onto U1, that's easy, and that right angle is going to give me what I want, because now all I have to do is climb back up from the projection to A2, and I have a vector that will be perpendicular to the span of U1, which is what I want. So now I just translate my geometric insights into algebra. My golden orthogonal vector is, well, it's A2 minus what? Minus this orange vector, which is the projection of A2 onto U1. And we know the projection of A2 onto a unit vector U1 is just A2 dotted with U1. That gives me the scalar by which I have to multiply U1 itself. And that's going to give me the vector pointing in the right direction. To make it unit length, I'm just going to normalize. And now this is just a bunch of computation. So let's see. We need to figure out what this vector is on top that we will then be normalizing. That's going to be A2, which is this vector, 5, 2, 2, 14, 10, and then I have to subtract off a certain multiple of u1, which we already computed. There's u1, but what is that scalar multiple? Well, that's a2 dotted with u1. So I have to take the dot product of these two vectors. And let's see, when I do that, I get 4 plus 0 plus 0 plus 6, so that's going to be 10. And I'll have to take this vector sum and divide by its own length. So I'll just say the length of, I'm just going to put little quotation marks indicating that it's the length of all this stuff, because I'm too lazy to write that down a second time. Anyway, that is going to be what upstairs? 5 minus 8, so minus 3 for the first component, then 2 and 14, and then finally 10 minus 6, which is 4, and then divide it by its own length. Well, let's see, what is the length of that guy? Oof, 14. Actually, that's not bad. I always remember 13 squared is 169. Reverse the last two digits, and you get 14 squared, which is 196. So 196 plus 4 is 200, plus 16 is 216, plus 9 is 225. And the square root of 225 is 15. So we have to divide that vector by 15, which gives us this stuff. And lo and behold, that is going to be u2. And we have it. We have found our two vectors that constitute an orthonormal basis for the span of A1 and A2. A two-dimensional subspace of R4. And so now, for example, if I wanted to take some vector in R4 and project it orthogonally onto that subspace, that would be a piece of cake because I have an orthonormal basis for it. I would just project onto each vector individually and sum the projections up, like we talked about last time. And that's it. There is nothing more to say, really, about the mysterious Gram-Schmidt process, which should be mysterious no more. And that means it is time for us to turn our attention to QR decomposition and learn what it is, how it relates to the Gram-Schmidt process, and why anybody cares about it. So, QR decomposition. What is it? Just as we can decompose a number into a product of simpler factors, or as we can decompose a polynomial into simpler factors, it is also the case that we can often take a matrix and decompose it into a product of simpler factors. And there are many different sorts of decompositions of matrices. For example, we have already discussed the idea of eigendecomposition, which allowed us to take any diagonalizable matrix A, in other words, a square matrix with enough linearly independent eigenvectors to form an eigenbasis, and rewrite it as a product of three matrices. And I'm not going to review what these all mean, except to remind you that they expose all the eigen stuff of the matrix. So it's like a nice X-ray of the original matrix. I only bring it up to remind you that this sort of decomposition, eigendecomposition, A, only held for certain types of matrices, diagonalizable matrices in particular, and B, is given by a very particular kind of structure. The middle matrix is diagonal, for example, and its diagonal entries are the eigenvalues of A. The first matrix contains eigenvectors corresponding to each of the eigenvalues. The third matrix is the inverse of the first matrix. That sort of thing. Anyway, QR decomposition is another sort of matrix decomposition, and it only holds for certain types of matrices. In particular, QR decomposition works for any matrix whose columns are linearly independent. So nothing too onerous in the demands that are placed on a matrix to have QR decomposition. It need not even be square. For example, here I have a 4x3 matrix. The columns of this particular matrix are indeed linearly independent. I will leave it to you as an exercise to demonstrate that that is true. It's very easy. But since the columns are linearly independent, it should have a QR decomposition. And like an eigendecomposition, a QR decomposition has a particular structure. The decomposition will consist of two matrices, which we call Q and R, and they will be of very particular types. The Q matrix will be a matrix with orthonormal columns. You might remember from back in chapter 6, I believe, I think I even mentioned that Q is the symbol that we often use for matrices with orthonormal columns. Back in chapter 6, we were specifically talking about square matrices with orthonormal columns, which are called, confusingly, necessarily orthogonal matrices, but in fact, we often use Q to denote a matrix of any size whose columns are orthonormal. And that's what the Q in QR decomposition is telling us. The second matrix in the factorization, R, is going to be an upper triangular matrix. That means in particular that R is going to be a square matrix. Q will actually have the same dimensions as the original matrix. So if we start with a 4 by 3 matrix, Q will also be 4 by 3, and to make the dimensions come out right, R is going to have to be a 3 by 3 matrix. All right, so we know that in a QR decomposition, which I'm claiming for now holds for any matrix with linearly independent columns, we can write that matrix as a product of a Q matrix and an R matrix. Q being a matrix whose columns are orthonormal, and R being an upper triangular matrix. Well, that's a bold claim. What would it look like if we did a QR decomposition here? Well, it would look like this. Never mind for now where this came from. We'll see that soon. We can see at a glance that the proposed matrix R is upper triangular. It takes a little more than a glance to see that the proposed matrix Q has orthonormal columns, but it does. It's easy to see that each one is unit length just by using the usual distance formula, and that sprinkling of negatives ensures that each pair of columns is an orthogonal pair. The dot product of any two columns is going to be 0. And if you take the time to multiply these two matrices together, you will indeed see that you get the one on the left. So this really is an honest-to-God QR decomposition of our original matrix. And as I said before, you can find such a QR decomposition for any matrix whose columns are linearly independent. That's the one condition that must be met. Okay, but this immediately gives rise to two very natural questions. The first of which is, who cares? I mean, is this kind of factorization just some kind of party trick, or does it have any particular application? And assuming we are able to get a satisfactory answer to the first question, the second natural question is why? Why is it that any matrix with linearly independent columns can be factored in this peculiar way? How do we know it's true? I've shown you one example, but does that really mean that it works for any matrix with linearly independent columns? How do I know that that will always hold? How do I find such a QR decomposition? Why am I making this assertion? Why? Why? Well, let's handle question 1 first. Who cares? People who design algorithms in computer programs that implement linear algebra definitely care about QR decomposition, because in many instances, having a QR decomposition of a matrix saves you a lot of computations down the line, and therefore your programs will run more efficiently. The easiest example to see how this works is to think about the humble problem of solving a system of linear equations, ax equals b. Now, we all know how to do this, of course. It's just a matter of Gaussian elimination, but that can be very computationally expensive if our matrix is very large. All right, well, let's suppose for a second that we happen to know a QR decomposition for our matrix A. Well, in that case, I could rewrite this equation as QR x equals b, where I've simply replaced A by QR. And let me remind you of what the QR decomposition asserts we can do. For any matrix A, whose columns are linearly independent, we have A equals QR, where Q's columns are orthonormal and R is upper triangular. So by factoring this A into QR, we've imposed some structure on these two factors. We know that R is an upper triangular matrix. We know that Q's columns are orthonormal. Well, matrices with orthonormal columns have some nice properties. We bumped up against these in chapter 6. The important thing here is that if Q has orthonormal columns, then it turns out that there's something very nice about the product Q transpose Q. What is this equal to? Well, think about what this would be. Matrix Q consists of a bunch of columns, which I'm representing here by different colors. Q transpose would be the matrix whose rows are the columns of Q. So I have the corresponding colors over here for the rows. Well, now think about what happens when we carry out that matrix multiplication. In particular, let's think about the entry perspective on matrix multiplication. In the product matrix, what would go in row 1, column 1? Well, that's the dot product of the first row of Q transpose and the first column of Q. Well, the first row of Q transpose is the first column of Q. That's what it means to be the transpose. So we are just dotting the first column of Q with itself. And when you dot a vector with itself, you get its squared length. Well, every column in matrix Q has length 1 because those are orthonormal vectors. So its squared length is 1. That means in entry 1, 1, we get a 1. What about in entry 1, 2, row 1, column 2? Well, that would be another dot product of the second row of Q transpose and, again, the first column of Q. But the second row of Q transpose is the second column of Q by definition of the transpose. So that means it would just be the dot product of these two columns. But the columns of Q are an orthonormal set. So if you dot any two distinct columns, you get 0. And it should be pretty clear that you're going to get zeros all the way down that first row, except for that initial 1. And you probably see where this is all going. If we look at the second row in the product matrix, well, the first entry is going to be this orange vector dotted with the green vector. But the orange and green vectors are columns of our matrix Q, so their dot product is going to be 0. Because the columns are orthonormal. You will always get a 0 when you dot two of these columns, unless it's a case where you are dotting one of the columns with itself. Like if I dot orange dot orange, I'm just going to get the squared length of orange, which is going to be the square of 1, which is going to be a 1. And that's what I would get in entry 2, 2. And you should be able to see that we will get 1s on the main diagonal and 0s everywhere else. And the moral of the story is that Q transpose times Q, where Q is a matrix with orthonormal columns, is simply the identity matrix. You probably recognize this in a more abbreviated form from Chapter 6, where we learned that if Q is an orthogonal matrix, if it's a square matrix with orthonormal columns, then the inverse of Q is Q transpose, and that's what we see right here. Q transpose is the matrix that you'd have to multiply by Q to get the identity matrix. But this is a little more general result, because we haven't made any mention of inverse matrices per se, because Q doesn't have to be a square matrix, and only square matrices truly have inverses. For example, if Q is a, say, 4x3 matrix, then Q transpose would be a 3x4 matrix, and then we'd have a 3x4 matrix times a 4x3 matrix. The inner dimensions match, and we would end up with a product that was 3x3. So this would be the 3x3 identity matrix. Different dimensions than what Q was originally. But anyway, this property is kind of the key fact about matrices with orthonormal columns. And the reason why we used a QR decomposition here in our system of linear equations is because then if we multiply both sides of the equation on the left with Q transpose Q becomes the identity matrix, which therefore isn't actually doing anything. And now the equation we're trying to solve is Rx is Q transpose B. But there's two things to bear in mind here. First, Q transpose B is still just a vector, some specific vector, just like B, the original right-hand side, was just some specific vector. But Rx on the left-hand side is a lot nicer to work with than AX, the original left-hand side, because R has a very specific meaning in this context. R is going to be an upper triangular matrix. So we still have something of the form, basically, AX equals B, which means that we can solve this by rewriting it as an augmented matrix. And it would look something like this, where I've got an upper triangular matrix on the left side of the bar, zeros below, of course, and on the right side of the bar, I just have some numbers because Q transpose B is, as we said, just some vector. But this is really easy to solve because we don't have to do any Gaussian elimination. We can solve this just by doing back substitution, like all the way back in Chapter 4 when we talked about ordinary row echelon form as opposed to reduced row echelon form. Once we have something in this form, the last row is going to be a bunch of zeros, one number here, and one number here, which means that we can immediately solve for the last variable, the variable corresponding to the last column. And once we have that, we can feed that value into the second to last equation, which will have only two entries on the left and a constant on the right. And we know the value of one of those entries. That means we can solve for the second one. And then we will know the value of the variable corresponding to the second to last column. We can take those two values, feed it into the row above that, and get the value of the third third to last row, the value of the variable corresponding to the third to last row, and keep going back until we have them all, with no need for the machinery of Gaussian elimination at all. So that's very nice, because Gaussian elimination is expensive. Back substitution is trivial. We could do that by hand. So if we happen to have a QR decomposition of a matrix, and we're trying to solve a linear system involving that matrix, QR decomposition is the way to go. So that gives you a sense of why we should care about such a thing, or why some people will care about such a thing. And that is not the only place where QR decomposition helps us with numerical algorithms related to linear algebra. There is another one, for example, involved in the problem of finding eigenvalues of a matrix. I think I said earlier in these lectures that arguably the two equations at the heart of linear algebra are AX equals B, which we just talked about, corresponding to any linear system, and AX equals lambda x, the eigenvalue equation. We saw how QR decomposition helps us solve this one. It also helps us find eigenvalues. I'm not going to discuss that in any detail because it's much more involved, but you will probably recall from chapter 7, when we talked about eigenvalues, I mentioned that the approach we used, looking at the characteristic polynomial and finding its roots, which actually are the eigenvalues of a matrix, is great for 2x2 matrices, okay for 3x3 matrices, and not so good for large matrices. So there are all sorts of eigenvalue algorithms for dealing with finding eigenvalues of large matrices. One of the most famous is called the QR algorithm, or something like that. The QR eigenvalue algorithm, which begins by finding the QR decomposition of matrix A and going from there. You can look it up if you're interested, but as I say, it's more involved than the kind of thing I showed you a moment ago, where we used QR to approach the equation AX equals B. And there are other uses of QR decomposition as well. A very important topic in numerical linear algebra. We are really only going to be talking about it in this one lecture. But as I said in the beginning, it's closely related to the Gram-Schmidt process in ways I have not yet described. So maybe I should add a third question on here. How does it relate to Gram-Schmidt? A much less fundamental question than who cares or why, but I'm obliged to answer that one because I brought it up in the beginning of the video. The answer to 3 is tied up with the answer to 2. So now that I think we have disposed of the who cares question, let's get into these questions, which really, as you will see, are interrelated. So I'm going to go ahead and erase number 3 since we're going to hit that en route to answering number 2. Why? Why is it that if I have any old matrix whose columns are linearly independent, I can decompose it into a product QR, where Q's columns are orthonormal and R is upper triangular? Why? Why can we do this? And how? Well, strap in and let's explore the details. Let's start with our matrix A, and all we're assuming about A is that its columns are linearly independent. Let's go ahead and give those columns names, A1, A2, all the way down to A sub k. And let's say that these columns are linearly independent vectors in Rn. There are k such vectors, so that means k must be less than or equal to n, so that this matrix is a n by k matrix, so not square in general. Now, because these k columns are linearly independent, their span is a k-dimensional subspace of Rn. Each one of the vectors contributes a dimension to the span. So that means that these k columns are in fact a basis for their span. I'll write that down here. They're linearly independent vectors, so they constitute a basis for their span. Or to state this in another way, they constitute a basis for the image of matrix A. Or as some people like to say, they constitute a basis for A's column space, which just means, of course, the span of its columns. All right, well, we have learned in the first part of this video how to take any old basis for a subspace and upgrade it to an orthonormal basis. Yes, we use the Gram-Schmidt process. So we could do that here. Let's let U1 through UK be the orthonormal basis for A's image that we get by applying Gram-Schmidt to the A vectors, to the columns of A. And maybe I should paint those U vectors green. Now we have have an orthonormal basis for the image of A? Well, one thing we've learned, and we discussed this a lot in the last video, is if we have an orthonormal basis for a space, any vector in that space is simply the sum of that vector's projections onto the individual orthonormal basis vectors. So that means, for example, A1, the first column in our matrix, is the sum of A1's projections onto those k individual vectors in the orthonormal basis. So remember, despite this complicated looking expression, that is still just one vector. It's just another way of writing A1, but it's going to reveal something important to us after an orgy of algebra. So that is just A1. We could do the same thing, of course, with A2, rewriting it as the sum of its projections onto each of the k orthonormal basis vectors, u1 through uk. And of course, there's nothing special about columns 1 and 2. We will do this with all of the k columns. All right, well, this looks very ugly, but not ugly enough. Not ugly enough. I'm going to take one step further into ugliness by making a simple observation, which is that since each column of the matrix is a weighted sum of the u vectors, you've got some scalar times u1 plus some scalar times u2, etc. Since that's the case, and I know that any weighted sum of vectors can be expressed as the product of a matrix and a vector, I'm going to do that for each one of these columns. Like, let's just concentrate on the first column first. Since the first column is a sum of the u vectors, I could express that as the matrix whose columns are those u vectors multiplied by a certain vector, which will consist of the weights that I attach to those columns. Well, those weights in the weighted sum are those scalar projections of A1 onto the orthonormal basis vectors. So A1.U1, A1.U2, and all the way down to A1.UK. That matrix vector product is that stuff, which is simply A1. So we've expanded little old A1 out into this matrix vector product, which is still just a vector, and therefore still just one column in this matrix, which in fact contains k columns. And we can do unto the second column as we did unto the first. And that, of course, will look like this. In our matrix vector product, we have the exact same matrix that we had in the first column, because this second column is a weighted sum of the exact same vectors. The only thing that has changed are the weights, and this time the weights are A2 dotted with all of the u vectors, whereas in the first case it was A1 dotted with all those u vectors. Do this for every column, and now we have this somewhat grotesquely expanded version of our original matrix. But fear not, we have reached the point of maximum expansion, and we can now begin to reel all this stuff in and contract it again, but into a new form. The key observation here is that since each column of this matrix, each of the k columns, has this form of a matrix vector multiplication, and the matrix is identical in each case, we can write this single matrix as a product of two matrices if we think about the column perspective on matrix multiplication. So reaching back into chapter 3, namely, we can write this stuff as the product of these two matrices. Remember the way that column perspective on matrix multiplication works. If I have one matrix times another, I can produce the columns of the product by successively taking the product of the left matrix by the various columns of the right matrix. And when I've done that for all of them, I have my product. So by that column perspective, this stuff is indeed equal to the stuff on the previous line. And now we've made some progress. Let me clean out the intermediate steps here. Okay, that's better. Now I have indeed factored A into a product of two matrices, and I claim that this is a QR decomposition. Let's begin with the Q. Clearly, this matrix on the left can serve as our Q, because Q is supposed to be a matrix whose columns are orthonormal. Well, the columns of this matrix are indeed orthonormal by construction. That's what we get out of the Gram-Schmidt process. Okay, so that part is done. That's easy. All that remains is to explain why this matrix on the right can count as our R matrix. For that, it has to be upper triangular, which means that all these entries, all these dot products below the main diagonal have to be 0. If we can demonstrate that, then this will be upper triangular. We can call it R, and we'll be done. So again, what I'm doing is we're looking at everything below the main diagonal, and we must explain why those entries are all zeros. If they're all zeros, then this is an upper triangular matrix, and we're done. We will have achieved QR factorization. Well, to understand why all of those entries will be zeros, we have to think back to the Gram-Schmidt process itself, because that's what we used to turn all those A vectors into U vectors. And the entries of this matrix on the right are all the possible dot products of A vectors and U vectors. Well, I think we can see this by thinking about it geometrically. Let's begin by concentrating on the first row of this matrix on the right. Those entries are all A1, the first column of A, dotted with each U vector. So each vector from the orthonormal basis that we got by carrying out Gram-Schmidt. Well, let me just sketch a picture down here reminding us of the first few steps in the Gram-Schmidt process. I've sketched A1, A2, and A3. Those are the first 3 vectors that appear as columns in our original matrix A. These vectors are linearly independent. That's what we assume from the beginning if we're trying to do QR decomposition. So I've drawn the plane that contains vectors A1 and A2, and then we know A3 is going to be sticking out of that plane since it is independent of its predecessors. Now, there may be more vectors to come, but I can only draw my picture convincingly when I have 3 or fewer vectors, so I'll just stick with 3, and that should be enough to spur our imagination to understand what happens when we have more. Anyway, if we carry the Gram-Schmidt process out on these 3 vectors, what happens? We start with A1. To turn it into U1, all we do is normalize it. We divide by its own length, and there we have vector U1. Now, how do we get U2? Well, we take vector A2, project it down orthogonally onto vector U1, but instead of just looking at that vector projection, we're going to subtract it from A2, which will give us a vector at right angles to U1, and then when we normalize that, it will become vector U2. So now we have the first 2 vectors in our orthonormal basis. What do we do with A3? You know the drill by now. You know it as well as Gram and Schmidt themselves know it. We drop a perpendicular, in other words, we project it down onto the subspace spanned by U1 and U2, namely this plane that I drew. But we're not interested in the projection for its own sake. We're going to subtract it from A3, which gives us a vector that is perpendicular to that 2-dimensional subspace. So in particular, it is perpendicular to both U1 and U2 that lie in that 2-dimensional subspace. Well, that's great. It's orthogonal to everything that came before it. So now all we have to do is normalize it, and now we have vector U3. And if there was a vector A4, a 4th column, well, you know how the process continues. But I'm going to stop there before my drawing gets too confusing. But everything still works out the same way. And this sketch should be enough to help us see what happens to all these entries. Let's go back to this first column where we're taking A1 and dotting it with all of the U vectors. Well, when we dot A1 with U1, what happens? Those vectors are pointing in the same direction. So their dot product is just the product of their lengths. So this is going to be some non-zero scalar. But that's not the one I'm interested in. I'm interested in all the ones that are below it, because they are all below the main diagonal. Like the next entry here, the first one I'm really interested in would be A1 dotted with U2. Well, U2 was designed to be perpendicular to the space spanned by U1, and A1 is in that space. So U2, of course, is perpendicular to A1. And since A1 and U2 are perpendicular, their dot product is going to be 0. And what about the entry below it? That would be A1 dotted with U3. Well, again, U3 was by design, by the very way the Gram-Schmidt process works. U3 is at right angles to the subspace spanned by U1 and U2. Well, A1 lies in that subspace. So when you dot those 2 vectors, you're going to get another 0. And I hope you see that's going to happen all the way down. By the time we get to UK, the last one, even if there are a million vectors in our original matrix, UK, the millionth vector in the orthonormal basis, was designed to be perpendicular to everything that came before. And A1 is in the span of everything that came before. So that means that UK dotted with A1 is going to be a 0. And if you understand that much, you understand how this is going to work all the way down. Because if we look at the second column, for instance, this is going to be A2 in each entry dotted with all the various U vectors. Well, A2 dotted with U1, well, that's just going to be some number. There's nothing really we can say about it. And in fact, A2 dotted with U2, well, again, that's just going to be some number, the product of the scalar projections of those two vectors onto U2. We don't care what that number is. But when we get to the next one, the first one below the main diagonal, which would be A2 dotted with U3. Well, U3, by design, by the Gram-Schmidt process, is perpendicular to the span of U1 and U2. Well, A2 lies in the span of U1 and U2. So that means U3 must be perpendicular to A2, so that entry would have to be 0. And similarly, A2 dotted with U4. Well, U4, wherever it is, sticking out into four-dimensional space, is, by construction, perpendicular to everything in the span of U1, U2, and U3. Well, that includes A2, which lies in that span. So that entry would be 0, and we would get zeros all the way down in that column. And indeed, that is going to continue all the way to the end. Anything below the main diagonal on this right matrix is going to be the dot product of one of the U vectors with one of the A vectors that lies in the span of the earlier U vectors, which by the Gram-Schmidt process are all perpendicular to the U vector in question. So that's where all those zeros come from. I hope you can see intuitively what is going on here. And since all the entries below the main diagonal are zeros, this matrix on the right is indeed an upper triangular matrix. So we can go ahead and call that R. And we have done it. We have demonstrated that every matrix A, which has linearly independent columns, can be decomposed into a product of a matrix with orthonormal columns and an upper triangular matrix. And we've even seen exactly what those two matrices are going to look like. Q is just the result of applying Gram-Schmidt to the columns of A. And R we get by taking a whole lot of dot products. In fact, really by taking every possible dot product between the A vectors and U vectors. But all the ones below the main diagonal turn out to be 0. And that is QR decomposition in a nutshell. And I guess we should do one very quick numerical example, which will be based on something we did already in this video. When we were discussing the Gram-Schmidt process, we finished up by looking at a numerical example where we had these two vectors, A1 and A2. These were two linearly independent vectors in R4, so they constitute a basis for a subspace of R4. And in our numerical example, we grammed the Schmidt out of those vectors, and the result was that we upgraded that basis for that subspace into an orthonormal basis, U1 and U2. And we carried out those details and computed exactly what the components of U1 and U2 must be. Well, to connect that Gram-Schmidt process to a QR decomposition, we could take our initial two vectors, A1 and A2, and make them the columns of a 4x2 matrix, whose columns, of course, are linearly independent. Any such matrix can be QR decomposed, and the result will be very easy to write down based on what we did before. We know that the Q matrix, the one with orthonormal columns, is going to be a matrix of the same dimensions as the one we started with, and its columns will be the two columns that were produced by this Gram-Schmidt process. So those will be like so, and our R matrix, our upper triangular matrix, is of course square. Only a square matrix can be upper triangular, and to make the dimensions work out right, that's going to have to be a 2x2 matrix, because if our initial matrix was 4x2, as is our Q matrix, and the R matrix has to be 2 by something to make those inner dimensions match, and since it's going to be square, it will have to be 2x2. And that way, of course, the product turns out to be 4x2, exactly as it ought to be. Anyway, what will the four entries of that 2x2 matrix be? They will be all the different dot products we can make of an A vector and a U vector. The one in row 1, column 1, A1 dotted with U1. And when we do that dot product, we get, 16/5 and 9/5. It's 25/5, which is 5. Now, moving over to row 1, column 2, that's going to give us A2 dotted with U1. And when we do that dot product, we get, 20, nothing, nothing, and 30 over 5. 5. So that's 50 over 5. So that is going to be 10. Down here, row 2, column 2, that corresponds to A2.U2, and when we do that dot product, we get minus 15, 4 is minus 11, 196 is 185, 40 is 225 over 15, which is 15, and this last entry we know is going to be 0, because this is, of course, going to be an upper triangular matrix. If you wanted to confirm that, of course, you could do the dot product of A1 and U2, you'd get minus 12 plus 12 is 0. Good, so that's it. We have successfully factored our matrix into a Q and an R. And now you can see why I put these topics together. Anytime you implement the Gram-Schmidt process, you basically get a QR decomposition of a matrix for free. All right. There are more things we could say. For example, in the exercises in the book, I point out that R, the upper triangular matrix, can be viewed as a change of basis matrix, going from the basis for the image of A consisting of the A vectors to the basis for the image of A consisting of the U vectors. Feel free to explain that one on your own if you wish, and if you don't, that's okay too. You can consider this QR decomposition material a kind of bonus, something you should be aware of in this, your initial tour of linear algebra, and something you may encounter later, but not really part of the main plot. Okay, next time we are going to talk about least squares, a very important application of linear algebra that I mentioned in the previous video. But until then, good night.